In Concept C, we're going to be focusing on our first set of periodic trends. We're going to be looking at atomic radius. So by the end of this lesson and in class, you should be able to describe nuclear charge, specifically effective nuclear charge, and also shielding, which involves electrons in the nucleus. You also should be able to determine and explain changes in atomic radii as well as ionic radii. So first I want to go back to the poll goal that you guys did on Coulombic attraction. So remember, this is the attraction between oppositely charged particles. So for example, when we talk about our protons that are positively charged in the nucleus and the attraction for the negatively charged electrons that surround the nucleus. And again, this is because they're oppositely charged particles, so it's going to cause an attraction between them. And this force can be weak or strong depending on a couple of factors. Now, one thing I also want to point out from the poll goal that you guys arrived at the very end is that it's important to know that the attractive force is not divided up by the electrons around the nucleus in the atom. Each electron gets approximately the full attractive force of the nucleus. However, we're going to look at what happens between the kernel electrons, so it's when there's interference between the nucleus and then the desired valence electron. But I just want to point this out because this is going to come up in a later slide, and I want you just to recall this from the poll goal that we already did. So we're talking about going across a period, which is going across a row from left to right. We want to remember that the nuclear charge is going to increase. We have additional protons. These protons are massive and they have a positive charge. And these basically kind of win the tug of war with the different electrons that are added in. Because as we go across a period, we're adding in a proton and we're adding in an electron. Which are tiny and negatively charged. So this nuclear charge increase is going to pull the electrons in more tightly, which is we're going to see cause some changes in atomic radii. Also, as we move across a period, shielding does not increase, and shielding occurs with our kernel electrons. Those interfere with the attraction between the protons in the nucleus and the valence electrons. So every element in the same period row has the same number of kernel electrons. And we're leaving out our transition elements in the groups 3 through 12, just focusing on groups 1 and 2, and then 13 through 18. So again, nuclear charge increases as we move across a period, but shielding does not. So because of these two factors, having a greater nuclear charge and no change in shielding, we can say that there's a greater effective nuclear charge. So there's a greater pull between the nucleus and the valence electrons. So again, just to recap, when we talk about effective nuclear charge, this is the amount of positive charge that actually acts on an electron. It influences all the periodic properties that we're going to talk about. So the greater the effective nuclear charge, the more pull on an electron toward the nucleus, and it also becomes harder to remove it, which we're going to tie into Concept D. So we've talked about moving across a period. Now we're going to move across, not across, but let's just say down a group. Now, our nuclear charge does increase because our number of protons increases. However, shielding does increase as we move down a group. Additional orbitals and principal energy levels means more kernel electrons are going to be interfering and blocking the attraction between protons and valence electrons. Because of this, there's a weaker attraction, which means the valence electrons are able to then drift further away from the nucleus. So keep that in mind as we talk about atomic radii. With those two effects, having an increased nuclear charge but having increased shielding, there's a smaller effective nuclear charge. So overall, there's less attraction between the nucleus and the electrons. Now, we talked about both nuclear charge and shielding. The one big point is when we go down a group, this is when shielding increases, and when shielding increases, that trumps everything. So even though we have a greater nuclear charge, the shielding is going to override that. So let's actually get into looking at atomic size and the atomic radius. Now, how we measure the atomic radius is by measuring half the distance between two neighboring nuclei of the element in the solid phase. And so we're able to then use the neighboring nuclei to determine the radius of one. When we talk about atomic radius, we're talking about the size of the atom. So the larger the radius, the larger the atom. Okay, so as we go down a group, the atomic radii is going to increase. And you can see as we move from lithium down to cesium, we have a larger atomic radius. As you move down a group, the number of principal energy levels is going to increase, and those just happen to take up more space, more electrons. This increases the distance between the valence electrons and the nucleus. So, for example, calcium is larger than magnesium because calcium has 4 energy levels and magnesium only has 3 energy levels, which contributes to calcium being a larger atom. And you can see here too with these graphics the additional energy levels. Potassium is larger than lithium, calcium is larger than beryllium, and so on. So again, just to recap, the new additional energy levels as you move down a group are occupied. So these additional kernel electrons are going to block the attraction between the nucleus and outer electrons. Our valence electrons then end up farther away, which increases the size and the atomic radii. So compared to lithium, this one valence electron only has 2 electrons blocking it in the nucleus. However, with sodium, we now have 10 electrons that are between the nucleus and the valence electron. So more shielding, they're blocking the attraction, so the valence electrons can be further away, increasing the atomic radius. All right, so we talked about going down a group. The atomic radii going from left to right is actually going to be decreasing as you go left to right across a period. So why does that happen? As you move across the period, the nuclear charge is going to increase. And there's the same number of energy levels, so there's no increase in the shielding. As the effective nuclear charge increases, there's going to be a stronger attraction between the nucleus and the valence electrons, which pulls them in closer. It's almost like making a larger magnet as we go across the period. Thus, because they're pulling them in closer, the radius is going to decrease, so the size of these atoms are decreasing from left to right. So you can see here with lithium, and then in the same period we have fluorine. Okay, we're actually going to get smaller because of, again, this greater effective nuclear charge that's pulling our electrons in. All right, so now we're going to switch gears a little bit and talk about ionic radius. We've talked about ions before. This is when they've lost or gained electrons. So now we just want to know what happens to the size of the ions. For metals, when they lose electrons and they become positive ions, the ionic radius is going to decrease. We have the same nuclear charge pulling on less electrons. Because our protons outnumber our electrons, the electrons are pulled closer to the nucleus. So we make a smaller ion. We also lose that whole valence shell. So it's almost like taking an onion and taking out the outer layer. Now that we have that one less layer, we have a smaller ion. Nonmetals are going to gain electrons to become a negative ion, and when this happens, the ionic radius is going to increase. We have the same nuclear charge pulling on more electrons, and while the attractive force doesn't get divided up by additional electrons, we went over that when we talked about Coulombic attraction. However, these additional electrons are going to repel each other, and they need more space because of that. So the electrons are going to actually drift farther away from the nucleus. And we can see here we have a nonmetal atom that's now gained an electron. Those valence electrons are going to move slightly further away from each other to get more space because of the various repulsions between them, thus increasing the size. Okay, so that's it for Concept C. I would go back and just quickly review the main trends of atomic radii going across the period and down a group, and also what happens when atoms gain or lose electrons, and what happens to the size of the ions. Okay, remember it all goes back to nuclear charge and shielding.